Good evening, this is Dr. Bijmohan. I am teaching physics in Department of Physics, Deshbandhu College. Today we will discuss the solution of hydrogen atom problem using finite difference technique. So the targeted equation for hydrogen atom has been represented by equation 1. Let's make a substitution by putting psi is equal to ur by r so that above equation can be written as into the radial wave function ur as follows. Now, to reduce different physical parameters present in this equation and to make this equation into the simplest form, we will introduce a quantity s which is equal to r by a naught, where a naught has the dimension of length. So by putting r is equal to s a naught in equation number 2 and doing simple analysis, we will reach to the equation number 7. In equation number 7, the value of epsilon naught is capital E upon 13.6 electron volt, which is again a dimensionless quantity. The denominator of equation number 6 has been calculated with the help of these parameters, which are in SI units. So this is the simplest form of equation number 2, in which each terms are dimensionless. Now we will apply the finite difference method to this equation. For simplicity, we will use the 6-point formula method to this equation. Let's discretize S into the 5 equal interval. Now, using the finite difference method, we have this equation in which the term L plus 1 by S square minus 2 by S is nothing but effective potential. Now, according to the boundary condition of hydrogen atom, the wave function at r is equal to 0 and at r is equal to infinity must vanishes. So, our interest is to calculate the wave function at S1, S2, S3 and S4. So by running j from 1 to 4 in the previous equation, we have the set of these equations. Now for S wave Schrödinger equation, L must be 0. Therefore, above equation can be written as. From above equation, we see that this is an eigenvalue problem which can be written as Hji ui is equal to epsilon uj, where Hij is nothing but Hamiltonian, which is defined as 2 by delta square plus v effective when I is equal to j, minus 1 by delta square when I is equal to j plus minus 1, and 0 at any other points. So now we will write the Python code for the hydrogen atom using finite difference method. First, we will import all the necessary libraries in Python. Next, we will define the potential. After this, we will give the different input parameters like what are the grid intervals, what are the initial points, what are the final points, and what is the value of delta. After this, we will discretize the R. Next, we will work for the Hamiltonian matrix. Here, for the off diagonal element, we will use this line, while for the principal diagonal element, we will use this line. Now, to calculate the eigenvalue and the eigenvectors, we will use this syntax. Finally, to plot all the wave functions, we will write these lines into the Python text box. In the end, we will print different values as calculated by the finite difference method, and to compare it with the theoretical one, we will print the theoretical value. However, we will also write the code for the plotting of different wave function for hydrogen atom. So after entering the number of intervals equal to 15,000, we will get these results. This result clearly explains that the calculated value are nearly equal to the theoretical one. So after running the Python code, we have the following results. In this graph, we have 5 wave function plots for hydrogen atom. In this graph, this curve represents the wave function for the ground state of hydrogen atom, while the orange one for the first excited state of hydrogen atom, and so on. From the figure, it is clear that ground state wave function has 0 nodes, while the first excited state has 1 nodes, and so on. So, in this way, we are able to calculate the approximate energy as well as the variation of different wave function of hydrogen atom using finite difference method in Python code. Thank you so much.